Hi, this is the first week of semiconductor engineering, and I'm gonna say with first energy band diagram. So energy band diagram is like this. So the lowest part and from electron, the in 0 Kelvin, the highest energy level that electron can have is the valence band edge. So we say this valence band, and the lowest level of the electron cannot exist. We say the conduction band edge. So we say this part conduction band, and the between of the conduction band and valence band, there cannot exist electron. There are no states from electrons. So we say this part forbidden gap, or we say this part is band gap. So this is the semiconductor energy band diagram, but like conductor, there are no forbidden gap. So the conduction band and valence band are put in together. So they they are they flow a lot, and the insulator like they doesn't flow well. The forbidden gap is too thicker, so the electrons on the valence band can excitate to conduction band well easily. So the medium gap, or we say that the semiconductor. So in silicon have four four electrons outside, so they have covalent bonding with, and they so usually in stable like this. But when we dope on it, like boron or arsenic, they have some free electron or one missing electron. So we say that's a hole. So there are like electron or a hole. For example, first, when we use boron, boron have five electrons on outside. So there are the four electrons have a covalent bonding with all silicon around, but one electrons are missing. So there have some free electron. So that we say that the free electrons carries on the energy, and so we say the major carrier are electron. So we say this n-type semiconductor. But when we use arsenic, like the materials with the three electrons outside, three electrons have some covalent bonding with silicon, but one are missing. So the other electrons come into here. So it feels the covalent bonding. But when the electrons move to here, there are one missing here. Then the one electrons comes move into here. So, but the electrons come move, and uh, there are like one holes. We can think like that. One holes moving to here. So we suppose some one things that are whole, and we say that the whole charge are plus charge. So we say like this, p-type semiconductor. The n-type semiconductor N come from negative, and p-type semiconductors P comes from positive because holes charge are plus charge and the electrons charge are minus charge. So this is the p-type semiconductor and n-type semiconductor. So we use this semiconductor on diode. We can say diode easily, PN junction. PN junction is like the type semiconductor and P type semiconductor, and we junction it, but it's actually not junction it. In whole semiconductor, we are partially doping in N-type and the others part are doping on P-type, but we can easily say this P-type and N-type semiconductor are junctioning, so we say this P-N junction, and when we say N-type here and P-type here, so this is the simple way to explain what is diode. So we have to know what is So we have to explain what is PN junction. So before we explain with the PN junction how it works, we have to know the energy band diagram. So I will draw an energy band diagram again. Energy band diagram is like this, as I mentioned. This part is conduction band, valence band, and this part is conduction band. And in 0 Kelvin, all of the electrons are in valence band. None of the electrons are in conduction band. And we say they're in 0 Kelvin and intrinsic semiconductor, the Fermi levels are the half of the forbidden gap. What is what is Fermi level is the probability of the electrons are 50%. So when we doped with n-type semiconductor, so n-type semiconductor, we say that the boron, like the outstates of the electrons are 5. We say that are donors because they give electron, so donor. So when we use donor to doping, the Fermi levels goes up to the conduction band because the electrons concentrations goes higher than the holes concentration. So the Fermi levels go like this. And oppositely, the P-type semiconductors, we say like arsenic or acceptor because they accept electrons. So they have higher concentration of holes than the electrons. So the Fermi levels goes lower and it goes to the valence band. So that's the Fermi level changings in the P-type semiconductor and N-type semiconductor. And how to draw a p-n junction energy band diagram is first, you have to draw a Fermi level constant. Why the Fermi level constant? Why Fermi level is to be constant? Because when the Fermi level is not constant, that mean there are different of electron concentration. So when there are different of concentration, they can have some diffusion current, but we are supposing at zero bias, so there are no current flowing on that PN junction. So we have to say the Fermi level is constant. So drawing like this is Fermi level. And as I said, n-type semiconductors, n-type semiconductors Fermi levels is closer to valence band. So like this is conduction band, and this is the valence band. And as I mentioned, p-type semiconductors Fermi levels are closer to the valence band. So like we can draw like this. And we have to draw some valence band like this. So this is the energy band diagram of PN junction. And what mechanism are now here? That is the special parts of PN junction. So what is happening here? We have to know about it. So I can draw another PN junction like this. This is the N type, and this is the P type. N-type have lots of electrons, and P-type have a lot of holes. And in the junction parts, the electrons and the hole recombine together, so they goes neutral. And as I mentioned, the electrons, so when the electrons go to here and P-type's holes goes to N-type, they diffuse to another to so because they have some different on concentration, because N-type have lots of electrons and P-type have a lots of hole. So when the electrons go to the P-type, they have some fixed donors fixed donors ion, because the N-type and P-types are actually quasi charge neutral, because the donor ions and the electrons are neutral, and the holes and the acceptor ions are neutral. But when the electrons go to the P-type, the donor ions are now fixed, and they are plus charge. And oppositely, the p-type holes go to the n-type, and the acceptor ions are fixed here. And there are no mobile carrier on this area. So we say this depletion region because there are no carrier, and we say there are none of current are flowing, but there are donors ion and acceptor ions on here, and the donors ion have plus charge, and acceptor ions have a minus charge. So there are plus, 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 minus, 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 and we have learned on electromagnetics the plus and minus. There are electric field on it. And there are drift current about here. So the plus and minus are going here, and the E field directions will go here, and the electrons will go p-type to n-type, and the holes will go n-type to p-type by the electric field. We say this drift current, and by the concentration, we call that diffusion current. So when the electric drift current and the diffusion currents goes equal, the diffusion regions go stopped, and there are some there are none of current flowing. So when the electric field happens, the balance band the energy band goes up. So the when I as I draw it, the energy band diagram of the PN junction, or like where's the so this the gradients happens because of the E field had happened, so it goes up. So this is the PN junction of energy band diagram, and next week I will explain are the what are the some things happens in the PN junction and the MS junction. So thanks to watching my video.